tornado just tore through the Texas Panhandle with tennis ball-size hail and 60-mile-per-hour winds, while 3 separate tornado warnings fired simultaneously across 2 states. Violent night, dramatic footage, scary radar, and meteorologists looked at all of it and said that was the weak one. The Storm Prediction Center has already issued back-to-back enhanced risk outlooks, and a rare Day 6 warning is now sitting over 22 million people, the same corridor. Again, the models predicted 3 waves. Wave 1 just verified exactly on schedule, which means the atmosphere just showed its hand, and what it's holding is considerably worse than what we've already seen. Stay with me, because what's coming next in this sequence should genuinely concern you. If this has hooked you, subscribe to the Skylab, because this outbreak is still unfolding and we are going to track every wave as it arrives. Also, drop a comment telling me where you are watching from and whether you think the 22 million people sitting inside this verified forecast corridor are prepared for what's coming their way. Now, let's get into it. Something touched down in the Texas Panhandle on the night of March 5th. 2026, and the word that keeps coming back to describe it is confirmation. Not surprise, not shock, confirmation. Because the meteorologists watching their screens that night had already seen this coming. They had already mapped it, modeled it, warned about it. And when the rotation appeared on radar near Quail in Collingsworth County, Texas, at 9:07 p.m. Central Standard Time, it wasn't the atmosphere doing something unexpected. It was the atmosphere doing exactly what it promised. A storm chaser captured the tornado on video. This matters more than it might sound. Radar can show rotation. Radar can show the swirling signature of a mesocyclone punching through the sky. But a confirmed tornado, one that gets officially classified under what the National Weather Service calls a torama, a tornado report and analysis, requires visual verification. Somebody has to see it. Somebody saw it. And what they saw was a real ground-scraping tornado tearing through one of the least populated corners of the Southern Plains on a Wednesday night in early March. The storm wasn't subtle about what it was doing. It threw tennis ball-size hail at the ground, which is not a casual statistic. To produce hailstones that large, an updraft has to be extraordinarily powerful. We're talking winds blasting upward inside the storm fast enough to keep an object the size of a tennis ball suspended in sub-freezing air while it builds layer after layer of ice. 60-mile-per-hour winds were reported alongside the tornado. The storm was tracking northeast at 30 miles per hour, moving toward Oklahoma with the kind of purposeful momentum that does not suggest it was planning to stop. And here's the thing that should have made everyone watching uncomfortable. At the exact moment the tornado was on the ground, 3 separate tornado warnings were active simultaneously across Texas and Oklahoma. 3 at the same time, and alongside those, 6 severe thunderstorm warnings were firing across Texas, Oklahoma, and Kansas all at once. The sky was not having one bad night in one county, the sky was having a system-wide breakdown across multiple states. Now the Texas Panhandle is sparse country. Collingsworth County doesn't have the population density of a major metro area, and that geographic fact almost certainly prevented this storm from becoming a catastrophe instead of a data point. But here is the part that the radar images, the warning counts, and the chase footage are all quietly screaming if you know how to listen to them. This was not the main event. This storm, this confirmed tornado, this tennis ball hail producer that fired 3 simultaneous tornado warnings and lit up 6 severe thunderstorm warnings across 3 states simultaneously, meteorologists had already classified this as the weakest wave in the sequence. 3 waves. That's what the models had been showing for days. 3 distinct pulses of severe weather organized into a single extended outbreak pattern. Wave 1 was always projected to be the least intense of the 3. It was always the opening move. And on the night of March 5th, Wave 1 verified. The forecast proved itself. The atmosphere showed its hand, which means the question sitting underneath all of that video footage and all of those radar signatures isn't whether the storm was violent. It clearly was. The question is, what happens when the stronger waves arrive? Because if this was the weakest one, the math on what comes next is deeply unsettling. Let's talk about what the radar was actually showing that night, because the confirmed tornado near Quail was only one piece of a much larger and more complicated picture on the screens at every National Weather Service office from Amarillo to Wichita. The dry line was positioned across western Oklahoma and the Texas Panhandle. And if you're not familiar with what a dry line is, imagine drawing a line on a map where everything to the west is desert air, dry, warm, low humidity, originating from the high desert plateau of the southwestern United States. And everything to the east is a completely different air mass loaded with Gulf moisture, humidity, that has traveled hundreds of miles north from the Gulf of Mexico and is just sitting there in the lower atmosphere, unstable and waiting. That boundary between the two is the dry line. And along that boundary on the night of March 5th, supercells were not forming in isolation. They were forming in clusters. Multiple rotating cells appeared along that dry line simultaneously, each one showing the Hooke echo signature on radar, that characteristic curved appendage hanging off the back of a supercell that tells any meteorologist watching that the storm is rotating, that there is a mesocyclone present, that the atmosphere inside that storm is doing exactly the kind of organized spiraling that produces tornadoes. Multiple storms, multiple Hooke echoes, multiple tornado potential zones at the same time, spread across a corridor that stretched from the Panhandle north into Kansas. The hail cores were equally telling. Tennis ball hail in Texas, golf ball hail in Oklahoma, quarter-size hail in Kansas. The gradient of hail sizes moving northward through the corridor is actually a snapshot of the instability levels at different points along the dry line, a map of how much energy the atmosphere had stored and was now releasing all at once. This is where the atmospheric anomaly starts to become impossible to ignore. In terms of the behavior, in terms of the structure of these storms, in terms of the instability producing those hail sizes and that rotation, this outbreak was behaving like late April, like the peak of tornado season. The kind of setup you expect somewhere around the 3rd or 4th week of April, when Gulf moisture is deep, when the sun has had weeks to heat the land surface, when the atmosphere has had time to build up the kind of thermodynamic profile that produces violent supercells. It is the 5th of March. This is the very beginning of the meteorological spring. Early March outbreaks do happen, but they typically come with smaller hail, weaker instability, less organized storm structures. What the radar was showing on March 5th was not a typical early March severe weather event. It was the atmosphere running 4 to 6 weeks ahead of its own seasonal schedule, producing the kind of storm structures that belong in late spring. 3 things had to come together to make that possible, and they all came together at once. Gulf moisture was streaming northward, unusually deep for this time of year. Wind shear, the change in wind speed and direction with altitude that gives rotating storms their spin, was strong throughout the entire atmosphere. And the dry line was providing the forcing mechanism, the trigger that lifts that unstable air, initiates the convection, and hands the storm the ingredients it needs to become violent. All 3 ingredients present, all 3 ingredients strong in early March. This wasn't just one bad storm in one unlucky county. This was a single local expression of a much larger atmospheric engine that had been building for days, that both major forecast models had been tracking with unusual confidence, and that was now entering its first verified phase. The storm near Quail was not the story. The storm near Quail was the proof. Step back far enough from any single storm, and you stop seeing a tornado, you start seeing a system. And on the night of March 5th, 2026, the National Weather Map was one of the most visually overwhelming displays of simultaneous atmospheric chaos that forecasters had seen in early March in recent memory. 604. That was the number of active National Weather Service alerts across the United States at the time of the outbreak. 604 simultaneously active weather advisories, warnings and watches covering every category the agency tracks. Tornado warnings in the southern plains, flood warnings across the Midwest and Ohio Valley, blizzard warnings in the northern tier, winter storm warnings across the Rockies and northern plains, fire weather warnings on the western side of the same system producing tornadoes in Texas. Read that last sentence again, slowly. The exact same storm system, one connected atmospheric structure, was simultaneously generating tornado warnings in Texas and fire weather warnings to its west, on the same map, at the same time. Because the dry line that was fueling the severe thunderstorms to its east was also marking the western boundary of extremely dry, low-humidity air mass that was sitting under gusty downslope winds, creating conditions where any spark could become a wildfire within minutes. Humidity values on the west side of that dry line had dropped to 6% in some locations. 6%. 8%. That is not a misprint. Denver was under a snowfall forecast from the cold side of the system's trough. The northern edge of the storm complex was dropping snow across the northern plains and the higher elevations of the Rockies, the classic winter storm signature. And simultaneously, the Midwest and much of the eastern United States was sitting under temperatures that were 30 to 40 degrees Fahrenheit above normal for early March. Some locations in the Midwest were reaching the 70s and even the low 80s in March, while blizzard warnings were active several hundred miles to the northwest. This happens because of the atmospheric pattern locked in place across the continent. A large trough, a southward dip in the jet stream, was positioned over the western United States, allowing cold Arctic air to push southward on its western flank and pulling warm Gulf air northward on its eastern flank. A strong ridge, an elevated dome of high pressure, was sitting over the eastern United States, blocking that cold air from moving east and allowing the warmth to build and persist. This ridge-trough configuration is one of the most favourable patterns possible for producing violent, severe weather. You get the warm, moist, unstable air you need on one side. You get the cold air reinforcement that sharpens the temperature contrast on the other. And where they collide, you get exactly what Texas and Oklahoma saw on March 5th. Across the Ohio Valley and the lower Missouri River Basin, rivers were already approaching flood stage before any of this new rainfall arrived. The Ohio River system, the Missouri River tributaries, streams and rivers through Indiana, Illinois, and Missouri, all of them were already running high. The ground in many of these areas was already saturated from earlier rainfall events in February and early March. There was nowhere for new water to go except into rivers that were already climbing. This was not a severe thunderstorm outbreak with some associated weather on the side. This was a continent-spanning atmospheric engine running simultaneously on every mode available to it: snow, wind, fire, flooding, tornadoes, with the central severe weather corridor representing just the most violent and visually dramatic expression of a system that was affecting essentially the entire country at once. And meteorologists had not been surprised by any of it. They had seen it coming, days before it arrived. Here's something that doesn't get enough attention when we talk about severe weather events. The storm near Quail didn't just happen. It was predicted, not in a vague something might develop kind of way. It was specifically predicted. The models had it, the timing had it, the ignition location along the dry line had it. And when the tornado touched down at 9:07 p.m. on March 5th, the meteorologists watching the data were not scrambling to understand what was happening. They were watching a forecast verify in real time. Both of the major global forecast models, the European Centre Model, known in forecasting circles as the ECMWF, and the American Global Forecast System, the GFS, had been showing strong agreement for days about what was going to unfold. Not just agreement about Wave 1, agreement about the entire three-wave sequence. First ignition along the dry line on March 5th, second wave pushing northeast toward the Midwest by March 7th and 8th, third wave reloading the Plains corridor sometime around March 10th through the 12th. Model agreement at that kind of extended range 5, 6, 7 days out is not guaranteed. Weather forecast models diverge. They show different solutions. Forecasters often have to navigate uncertainty and communicate probabilistic outcomes because the models themselves are not sure. When the European and American models converge on the same scenario at the same timescale with that level of specificity, it means something important is happening in the large-scale atmospheric pattern. It means the forcing, the big-picture meteorological mechanisms driving the weather, is so strong and so well-defined that both modeling systems are reaching the same conclusion independently. The Storm Prediction Center, which is the National Weather Service office responsible for convective outlooks across the contiguous United States, issued an enhanced risk on their Day 1 outlook and their Day 2 outlook back-to-back. Back-to-back enhanced risks in early March are not common. The enhanced category sits above slight and below moderate on the SPC risk scale, and when it appears in consecutive daily outlooks, it signals that forecasters are tracking a multi-day severe weather corridor, not a single-day event. It signals that the atmosphere isn't going to reset between storms. The energy is going to persist. And it has. Wave 1 verified exactly when the models said it would, exactly where they said it would, along the dry line in the southern plains on the 5th of March, which is the part of this forecast verification that should make you pause because model verification cuts in both directions. When Wave 1 verifies on time and on target, it increases the confidence that Waves 2 and 3 are real. It's not a guarantee. Forecasting still involves uncertainty. But when the atmosphere does exactly what the model said it would do for Wave 1, forecasters take the Wave 2 and Wave 3 projections considerably more seriously. Wave 2 wasn't targeting the sparse Texas Panhandle. Wave 2 was targeting populated cities, and it was already in motion. Every severe weather outbreak has geography. The storms don't know or care where they're going, but the humans tracking them care deeply. Wave 1 moved through one of the least populated regions of the Southern Plains. Collingsworth County, Texas does not have major cities in the path of a tornado outbreak. What it has is open land, scattered ranches, and the kind of sparse human footprint that makes a confirmed tornado a data point rather than a catastrophe. Wave 2 had different geography. The Storm Prediction Center's enhanced risk zone for the Wave 2 event shifted northeast into a considerably more populated region. Eastern Oklahoma, eastern Kansas, western Missouri, northwest Arkansas. This is not open panhandle country. This is a corridor that includes Kansas City, a metropolitan area of more than 2 million people, Fort Smith, Arkansas, Springfield, Missouri, Fayetteville and Bentonville in northwest Arkansas, which have seen significant population growth in recent years and represent a rapidly expanding urban footprint directly in the projected storm corridor. The SPC placed a 10% hatched tornado probability zone within that enhanced risk area. The hatching is significant. In the Storm Prediction Center's probability system, a hatched overlay on a tornado probability contour indicates that the forecasters are specifically flagging the potential for significant tornadoes, EF2, or stronger on the enhanced Fujita scale. EF2 means wind speeds of 111 to 135 miles per hour. These are not tornadoes that damage trees and strip shingles. These are tornadoes that destroy well-built homes and turn any vehicle in their path into a projectile. Discrete supercells were expected to fire in the late afternoon hours, following the classic severe weather initiation timing when the day's heating has maximized the instability in the lower atmosphere. And then, as evening arrived and the initial supercell mode began to organize, forecasters were watching for the storm mode to evolve, to shift from discrete rotating supercells into a more linear structure, a squall line pushing eastward into the nighttime hours. That transition matters enormously, and not just because a squall line can still produce tornadoes. It matters because of timing, because of what happens when severe storms move into densely populated areas after dark. The contrast between Wave 1 and Wave 2 is stark. A tornado in the Texas Panhandle at 9 p.m. on a Wednesday is a serious meteorological event. The same tornado, or something stronger, moving through the eastern suburbs of Kansas City, or the neighborhoods of Fayetteville at 2 in the morning, is a different category of emergency. The atmosphere was about to remind several million people of that difference. There is a particular kind of danger that doesn't show up easily in meteorological statistics, but it shows up very clearly in fatality records. Nighttime tornadoes kill more people per event than daytime tornadoes. This is not because they are physically stronger, it's because of a sequence of failures that compound on each other in the dark. People are asleep. The outdoor warning sirens that many communities rely on as their primary alert system, those sirens are designed to warn people who are outside. They are not particularly effective at penetrating walls, closed windows, and the deeper sleep that comes in the early morning hours after midnight. Wireless emergency alerts can reach phones on nightstands, but phones get silenced, set to Do Not Disturb, or simply don't wake people deeply enough for them to react in time. And even when the warning reaches someone, the night itself becomes a tactical problem. You cannot see the rotation. You cannot look out the window and watch the sky and make a real-time judgment about your danger. The storm is invisible. You are making decisions based purely on what a warning system is telling you in the dark, half awake, trying to move family members to interior rooms while something you cannot see is potentially minutes away. The Wave 2 storm sequence was expected to undergo exactly the kind of overnight evolution that meteorologists find most concerning. Discrete supercells firing in the afternoon, potentially producing large hail and tornadoes during the daylight hours when people can see and react. And then, as the night deepened, those supercells potentially merging or evolving into a quasi-linear convective system, a QLCS, a squall line that can still embed tornadoes within it. often brief, difficult to detect on radar until they're already on the ground, moving into populated areas while most of the metro is asleep. The low-level jet plays a role in this that most people don't know about. There is a counterintuitive reality in plain severe weather meteorology. The low-level jet stream, a ribbon of fast-moving wind in the lower atmosphere, typically around 1,000 to 2,000 feet above the surface, actually strengthens after sunset. As the boundary layer stabilizes, as surface heating shuts down at night, the wind maximum in the low-level jet increases. It feeds more moisture into the storm system. It increases the directional wind shear in the lower atmosphere, which is exactly the wind shear that controls tornado potential in squall lines. The storms don't necessarily weaken after dark the way the public assumes they do. In certain setups, they get worse. Forecasters watching the Wave 2 scenario were not reassured by the overnight timing. They were concerned by it. And with 22 million people already flagged in a Day 6 warning for Wave 3 still approaching, the concern was about to compound even further. The Storm Prediction Center issues severe weather outlooks for days 1 through 8. That range exists on paper. In practice, the Day 6, Day 7 and Day 8 outlooks are typically low probability, hedged forecasts that simply acknowledge the existence of some severe weather potential in the distant future. They are rarely the kind of forecast that commands immediate attention. They exist because the models show something, but confidence is usually low enough that the specific probabilities are modest and the geographic areas are broad. On this cycle, the Day 6 outlook was different. The Storm Prediction Center placed a 15% severe weather probability zone in their Day 6 forecast. 15% at 6 days lead time is not a hedged, low-confidence placeholder. That number at that range reflects genuine model agreement about a significant severe weather threat. It reflects the kind of persistent, well-organized, large-scale pattern that gives forecasters enough confidence to put a real number on a forecast that far in advance. The area covered by that 15% probability included Texas, Oklahoma, Kansas, Missouri, and Arkansas. The population exposure within that zone has been estimated at approximately 22 million people. Dallas and Fort Worth are inside it. Austin is inside it. Oklahoma City is inside it. The same corridor that was struck by Wave 1, the same corridor being targeted by Wave 2, it was already being flagged for a third hit, days before Wave 2 had even arrived. The projected timing for Wave 3 was March 10th through the 12th. That means the plains and the Midwest were looking at 3 significant severe weather events within a single week. 3 distinct pulses of organized severe weather drawing from the same persistent atmospheric pattern, reloading along the same boundary, targeting the same geographic corridor with increasing population density on each subsequent pass. Meteorologists who work these outbreaks professionally used language in their forecast discussions that reflected genuine concern, not the cautious, carefully hedged language of routine severe weather communications, the kind of language that appears when forecasters are watching a pattern that they recognize as dangerous at a level beyond the individual storm. Repeated impacts, same corridor. Soils already wet, rivers already elevated. 3 waves in 1 week. This was the kind of pattern that makes the people who do this for a living sit with a second cup of coffee at 11 p.m. and stay at the keyboard longer than they planned. And the reason the pattern existed at all, the reason Wave 1 verified, the reason Wave 2 was targeting cities, the reason Wave 3 was already flagged, came down to something happening at the very top of the atmosphere that was refusing to move. Before the second and third waves of storms arrived, the ground in much of the central and eastern United States was already making a quiet argument for why this outbreak could end up being more dangerous than the tornado headlines suggest. Because tornadoes are visible. Tornadoes are dramatic. Tornadoes command attention. Flooding kills more people per year in the United States than tornadoes do, and flooding was already in motion. 51 flood warnings were active across the central United States before Wave 2 made landfall. 51. Rivers across Missouri, Ohio, Indiana, and Illinois were already rising, fed by weeks of above-normal precipitation and February rain events that had saturated the soil across much of the region. The Big River at Burnsville in Missouri was projected to reach 22.4 feet at flood stage. Individual rivers in multiple states were either at or approaching flood stage simultaneously. The concept that meteorologists use to explain why this matters so much is called antecedent moisture. It refers to the moisture conditions that already existed in the soil before a new rainfall event begins. In a normal soil moisture environment, when rain falls, some portion of it infiltrates into the ground. It moves through the soil column, recharges aquifers, moves slowly. Flooding still happens, but the soil itself absorbs a portion of the input before runoff begins. In a saturated soil environment, after weeks of above normal precipitation, the soil has no more capacity to accept water. Rainfall does not infiltrate, it runs off immediately, directly into streams and rivers that are already elevated. The river response is faster, the flood peaks are higher, the flooding extends farther downstream, and now consider what happens when training thunderstorms develop in this environment. The National Weather Service office in Houston had flagged the risk of training thunderstorms, a pattern where individual storm cells repeatedly organize and move over the same geographic area in sequence, like freight cars on the same stretch of track. Each storm cell adds another inch, another 2 inches of rain on the same spot that the previous cell already soaked. The ground cannot absorb it. It runs off immediately into already swollen streams. Flash flood emergencies can develop rapidly even from storms that might look relatively modest on radar. The tornado that touched down near Quail on March 5th will be photographed and studied. The flooding that follows in the days after waves 2 and 3 move east will affect more homes, displace more families, and cost more in aggregate damage than any single tornado in the sequence. It just won't look as dramatic on radar. And by the time Wave 3 finishes its pass through the same corridor, the soils will have received a week's worth of moisture events on top of already saturated ground. 3 waves through the same corridor. Soil that cannot absorb more water. Rivers that started the week already climbing. This is the part of the story that will matter after the tornado warnings expire. More everything that's happened so far. The tornado near Quail, the back-to-back enhanced risks, the Day 6 warning, the flooding already in motion, all of it traces back to a single atmospheric configuration that was locked in place across the Northern Hemisphere and refusing to move on a normal schedule. The jet stream was stuck. The pattern in place was a trough in west, ridge in east configuration, which is exactly the setup that produces the most favorable conditions for severe weather in the central United States. The jet stream had amplified into large waves, deep southward dips, and high northward bulges, instead of maintaining the relatively flat, rapidly moving pattern that normally characterizes winter and early spring. And crucially, this amplified pattern had been persisting far longer than typical. Under normal atmospheric dynamics, jet stream patterns shift every 2 to 3 days. A ridge builds, it gets disrupted, a trough moves through, the pattern resets, weather sequences advance. Normally this cycling prevents any single weather pattern from dominating a region for more than a few days at a stretch. When the jet stream locks into a persistent, amplified configuration and refuses to cycle normally, you get what meteorologists call a blocking pattern. The weather pattern gets stuck. And whatever that pattern is producing, heat waves, cold waves, or in this case, repeated severe weather setups, it produces them again and again in the same corridor because the atmospheric engine is drawing from the same source of energy without refreshing its position. The current models were showing this pattern persisting for 7 to 10 days. 7 to 10 days of the same trough positioned over the western United States, funneling warm Gulf moisture northward and maintaining the vertical wind shear necessary for severe storms, while the eastern ridge keeps warm air locked in place across the Midwest and prevents any atmospheric reset. This is the mechanism. This is the reason Wave 1 was followed by Wave 2 was followed by Wave 3. Not coincidence. Not 3 separate storms. One persistent blocking configuration generating repeated severe weather cycles along the same corridor, like a machine that has been switched on and is not yet ready to turn off. Meteorologists and atmospheric scientists are actively studying the upstream drivers that caused this particular pattern to lock in place as early and as persistently as it did. The answers they're exploring get into territory that is genuinely not fully resolved in the scientific literature. While the jet stream was providing the structural framework for these repeated severe weather events, the actual energy fueling each individual storm wave was coming from something much closer to the ground. The warmth across the central and eastern United States in early March 2026 was extraordinary by any reasonable seasonal standard. Temperatures across the Midwest were running 30 to 40 degrees Fahrenheit above normal for the first week of March. Some stations recorded temperatures in the mid-70s. A few locations touched the low 80s. In the first week of March, while blizzard warnings were active several hundred miles to the northwest in the same weather system. This is not typical seasonal variability. This is the kind of temperature departure that registers as an anomaly, even by the standards of a warming climate baseline. The connection between that warmth and the storm violence isn't abstract. Warm air holds more water vapor than cold air. This is fundamental atmospheric physics. A warmer than normal lower atmosphere in March means more moisture is available in the air mass, even if the Gulf moisture transport were identical to a typical March pattern. When you then add unusually strong Gulf moisture transport on top of an already anomalously warm air mass, you are loading the atmosphere with an amount of thermodynamic energy that simply does not normally exist in this region at this time of year. That energy is what produced the tennis ball hail near Quail. The updraft strength required to suspend a hailstone that large reflects the available convective energy in the atmosphere, the CAPE, or convective available potential energy, at the time the storm formed. The CAPE values observed in this outbreak were values you typically see in late April or May in the southern plains, weeks ahead of seasonal norms. And here is what makes this particularly relevant to the three-wave outbreak sequence. The warmth didn't disappear after Wave 1. Even after cold front passage associated with Wave 1 moved through, temperatures in the warm sector east of the dry line remained above normal. The reservoir of atmospheric energy was not depleted by the first storm. It reconstituted. The Gulf moisture transport continued. The warmth persisted, which is precisely why Wave 2 could draw from the same instability profile that Wave 1 had exploited, and why Wave 3 was being set up to do the same thing a week later. The fuel for each wave in this sequence was being continuously replenished by the same anomalous warmth that had characterized the entire early March pattern. There is a boundary that shows up on almost every major tornado outbreak across the southern plains, a line that you would barely notice if you drove across it in a car, but that represents one of the most violent atmospheric transitions on Earth. On the west side of that line, the air is dry, sometimes extraordinarily dry. Humidity values at 6% on the afternoon of March 5th, 2026. Desert air that has traveled east from the high plateaus of New Mexico and Arizona, descending off the Rockies, warming and drying as it goes, wind gusts under red flag fire weather conditions. The kind of air that turns a spark into a 100-acre fire in the time it takes to make a phone call. 30 miles to the east, the air is completely different. Humid, warm, loaded with Gulf moisture, unstable enough that a small trigger is all it needs to explode upward into a towering cumulonimbus. The boundary between those two air masses is the dry line, and along that boundary the atmosphere is wound as tight as anything in meteorology gets. The dry line acts as the trigger mechanism for severe storm initiation across the southern plains. It is where the forcing concentrates, where the collision of completely different air masses creates the lifting necessary to launch warm, unstable air upward rapidly enough to initiate convection. When the larger atmospheric pattern is favourable, when the jet stream is positioned correctly, when the wind shear is strong, when the moisture is deep, the dry line becomes the ignition switch for the entire severe weather season. It is not coincidental that the most tornado-prone region on Earth sits directly in the zone where the dry line routinely positions itself each spring. The geography of Tornado Alley is the geography of the dry line. And on March 5th, the dry line was positioned exactly where the models had predicted it would be, providing the trigger for Wave 1 just as it was predicted to do, and already repositioning for Wave 2. The fire conditions to the west and the tornado conditions to the east coexisting along the same boundary on the same day is not a paradox. It is a description of how the dry line works. It is the boundary between two worlds, and on both sides of it, the atmosphere was expressing its energy in the most extreme form available. This is the ignition mechanism that each of the three waves in this outbreak needed. And it was going to be there for Wave 2 and Wave 3 just as it had been there for Wave 1, because the larger pattern keeping the dry line locked in position hadn't moved. Meteorologists and atmospheric scientists were not simply accepting the persistence of this jet stream configuration as a random atmospheric event. They were asking the harder question, the one that sits underneath the forecast data and the model outputs and the verified wave sequences. Why is this happening? What is driving a blocking pattern of this intensity and duration in early March, causing the atmosphere to behave in ways that belong to a different part of the season? The leading hypotheses being explored involve several large-scale climate signals that are known to influence the jet stream's behavior. The Madden-Julian oscillation, a propagating pattern of enhanced and suppressed atmospheric convection that moves eastward around the tropics roughly every 30 to 60 days, was in an active phase that some researchers were flagging as a potential contributor to the jet stream amplification. When the MJO is in certain phases, it can enhance the amplitude of Rossby waves in the jet stream, creating larger ridges and deeper troughs, and pushing the pattern toward exactly the kind of blocking behavior observed here. Polar vortex dynamics are another area of active investigation. When the polar vortex, the large-scale cyclonic circulation that normally contains cold Arctic air near the poles, experiences disruptions, it can send displaced lobes of cold air southward while allowing the jet stream to adopt more amplified wave patterns at lower latitudes. Stratospheric sudden warmings and their downstream effects on surface weather have been increasingly studied as drivers of persistent, extreme weather patterns. Sea surface temperature anomalies in the tropical Pacific and Gulf of Mexico were also being examined as potential modulators of moisture transport and atmospheric wave behavior. The ocean temperatures were anomalous in ways that some researchers believe can project significant influence on mid-latitude weather patterns weeks to months in advance. What all of these hypotheses share is honest uncertainty. The exact mechanism that caused this particular pattern to lock in place so early and persist so long was not fully resolved. What was resolved, what the data from March 5th had now demonstrated beyond any doubt, was that whatever was driving the pattern had locked the atmosphere into a sequence of storms that was now unfolding exactly as predicted. The theoretical questions about why were legitimate and important. But the practical question of what was coming next had already been answered by Wave 1 verifying on schedule. By the time the second wave was finishing its pass through the population corridor from eastern Oklahoma to northwest Arkansas, the attention of every forecaster watching the three-wave sequence had already moved ahead in time. Because Wave 3 was not a speculation. It was a projection backed by the same model agreement that had correctly predicted Waves 1 and 2, and it was targeting the same corridor with nearly identical setup ingredients. Wave 3 was projected to unfold between March 10th and March 12th. Approximately 1 week after the first tornado touched down near Quail, Texas, the atmosphere was expected to reload the dry line, regenerate the favorable shear profile, reconnect the Gulf moisture transport, and fire another round of severe storms across essentially the same geographic area that had already been hit twice. The difference was the baseline conditions it would be working with. By the time Wave 3 arrived, the soils across much of the central United States would have received rainfall from both Wave 1 and Wave 2. Rivers already at or near flood stage before Wave 2 would have risen further. The antecedent moisture conditions that had already made flooding dangerous before Wave 2 would be worse before Wave 3. Any flash flooding associated with the third event would have less buffer, faster runoff, higher peaks. On the severe storm side, the setup for Wave 3 was being described by forecasters as concerning. The same low-level jet that had fueled Waves 1 and 2 was projected to strengthen again for the Wave 3 event. The same dryline boundary was going to be available as a triggering mechanism. The thermal instability, the atmospheric energy that Wave 1 had drawn from so explosively that it produced tennis ball hail in early March, was expected to be present again in Wave 3, possibly enhanced by additional Gulf moisture deepening in the days between events. Forecasters who had been tracking the pattern described it as a scenario where the atmosphere was not given the opportunity to reset between events. In a normal severe weather sequence, a strong outbreak depletes some of the available instability. The cold front stabilizes the air mass and there is a recovery period before conditions become favorable again. This pattern was not providing a meaningful recovery period. The energy kept coming. The moisture kept flowing northward, The trough stayed in the west, and the corridor kept reloading. 3 times in 1 week, the same people in the same cities looking at the same warning polygon on the same National Weather Service website for the 3rd time in 7 days. Fatigue sets in. Warning fatigue is real and documented. People who have already evacuated or sheltered twice in a week make different decisions about whether to respond to a 3rd warning. And forecasters know this, which is part of why the Wave 3 outlook carried language that was not routine. And then the models showed something that added one more layer to an already extraordinary atmospheric story. Both the European and American forecast models, the same models that had correctly predicted the timing and structure of all 3 storm waves, were showing with moderate confidence a dramatic pattern shift beginning around March 16th through the 17th. After a week of tornadoes, flooding, and March temperatures in the 70s and 80s, the same jet stream pattern that had been producing the storm sequence was projected to slam into reverse. The trough would deepen dramatically. Arctic air from Canada would push southward with unusual force. Temperature departures that had been running 30 to 40 degrees above normal for 2 weeks would swing to potentially 30 degrees below normal within a matter of days. 60 to 80 degree temperature drops within a single week. That is not a seasonal transition, that is an atmospheric whiplash. Locations that were recording temperatures in the upper 70s during tornado outbreaks could potentially be recording temperatures in the 20s, possibly with snow within 10 to 12 days of those same tornado events. The forecast confidence for this pattern shift was still moderate at the extended range. 7 to 10 day forecasts for sharp pattern changes carry uncertainty that shorter range forecasts do not, and forecasters were careful about communicating that caveat. But the agreement between the 2 major modelling systems on the general character of the change, a sharp dramatic reversal from an anomalously warm and stormy regime to an Arctic cold pattern, was itself significant. When both models say the same thing about a large-scale change that far in advance, it usually means the large-scale atmospheric dynamics that would drive such a change are already in motion. The same jet stream amplification that produced the blocking pattern, allowing 3 storm waves to unfold in 1 week, would, under this scenario, ultimately generate the wave amplitude necessary to pull Arctic air southward with enough force to end the warmth dramatically. The storm sequence and the Arctic reversal were not separate events. They were consecutive chapters in the same story of an amplified, locked jet stream working through its pattern cycle. Tornadoes in the 2nd week of March, potentially snow in the 3rd week of March, in the same cities, from the same atmospheric pattern. That is a description of what an amplified, blocking jet stream does to the communities sitting underneath it. On the night of March 5th, 2026, while the tornado was on the ground near Quail and 3 warning polygons were lit up across Texas and Oklahoma, the event was one piece of a 24-hour window that stacked up other notable events in a way that made even routine news coverage feel slightly surreal. A magnitude 4.9 earthquake struck Louisiana during the same window. Not a catastrophic event, not a threat to life, but a notable seismic event in a region that attracts attention when the ground moves. Independently, a G1 geomagnetic storm was hitting Earth's magnetosphere, generated by a solar wind stream from a coronal hole on the Sun's surface. Solar wind particles interacting with the magnetosphere at those activity levels are enough to produce high-latitude auroras and minor interference with satellite systems and radio communications. On the same night that 604 weather alerts were active across the United States, these events were not connected. Earthquakes are not caused by tornadoes, geomagnetic storms are not caused by dry lines. The solar wind was indifferent to what was happening in Collingsworth County. They were separate physical systems operating on entirely different scales, following entirely different dynamics, intersecting only in time. And yet, there is something about the convergence of planetary events on a single calendar window that forces a moment of perspective. The tornado near Quail was not the entire story of that night. It was one thread in a planetary moment that included the ground shaking in Louisiana, the magnetosphere ringing from a solar wind impact, blizzard warnings in the north, and fire weather warnings in the west. The severe weather outbreak was unfolding during a moment of unusually intense activity across multiple systems simultaneously. It does not change the meteorology, but it does change the feeling. Let's come back to where we started. 9:07 p.m., March 5th, 2026. A tornado confirmed on the ground near Quail, Texas. Storm chaser video. Torama classification. Tennis ball hail. 60-mile-per-hour winds. 3 simultaneous tornado warnings across 2 states. That event is going to be referenced in weather records as part of this outbreak. It may get a paragraph in the monthly climate summary. It will be documented in the SPC's Storm Reports archive. And a few weeks from now, when someone searches for information about early March severe weather events, they will find it. But here is what those records may not fully capture. That tornado, that verified, documented, genuinely violent tornado in one of the sparsest counties in the Texas Panhandle, it was the weakest wave. The forecast models said 3 waves. Wave 1 verified on time, on target, with extreme instability for early March, producing the kind of storm structures that belong in late April. Wave 2 moved northeast into a corridor containing millions of people, with overnight timing and potential for EF2 or stronger tornadoes inside a squall line evolving in the dark. Wave 3 was already flagged in a rare Day 6 outlook. A 15% severe probability for 22 million people across Texas, Oklahoma, Kansas, Missouri, and Arkansas, scheduled to arrive in the same corridor that waves 1 and 2 had already hit, on soils that would no longer be able to accept any more rain. Underneath all of it, the jet stream remained locked. The warmth continued fueling the instability. The dry line kept repositioning as the trigger. The rivers kept rising. And the same 2 forecast models that predicted this entire sequence, the same models that were correct about Wave 1, were showing an Arctic reversal on the other side of it that would drop temperatures 60 to 80 degrees within a single week. This is not an extraordinary early March thunderstorm. This is not a typical first severe weather outbreak of the season. This is a multi-wave, week-long, continental-scale atmospheric event that arrived with more meteorological documentation behind it than most historic outbreaks carry. The forecasters knew, the models agreed, the atmosphere verified. The tornado near Quail may end up being remembered not as the main event of the first week of March 2026, but as the moment the atmosphere proved that everything the models had been predicting was real. The opening act of a storm sequence that was never going to be contained in a single evening, a single county, or a single news cycle. The first wave looked like this. Now count to 7 days, and keep watching the sky.